Hey, welcome back. So lately I've been working on things like this. I get that to focus. And this. These little feathery earrings. And I like them pretty well. The only problem is that I have a lot of trouble looking at the work when I'm really close to it. So I got myself a little flashlight. It just helps me out seeing stuff in the garage. And I really like it. It runs off one AA. The only problem is that it doesn't stick to my hat. So I can't actually aim it without putting it in my teeth, and I don't like holding it in my teeth. So what I did was I designed this little clip. And so this is just an old hacksaw blade. It's in two pieces, and you can see pretty easily that it's just brazed in the center. I used an oxypropane torch, and I heated it up until a yellow heat, and then just put a little piece of copper wire. I used borax as flex, and it stuck together pretty good. Now, a hacksaw blade is tool steel the whole way through. This wasn't a bimetal blade or anything like that. And that's usually pretty durable. It makes a pretty good spring by itself. The only problem with that is if you don't have a heat treat on it, it does tend to bend a little bit. So I can just show you how that works. It just slips over the front and kind of grips on there, and then I can put that as part of my hat, or I can flip it around, do whatever I need. So like I said, this works pretty well. The only problem is that it does tend to deform a little bit when I push it to its limits. So I need to put a heat treat on it. What I didn't tell you is that I had one of these before, and I tried to put a heat treat on it just with my little MAP gas torch, and the only problem with that is that the torch isn't really consistent. So what happened is this hardened really well, got super hard, couldn't scratch it with a file, and I tried to temper it to a blue color, but this mass of copper in the center actually sucked up all the heat in this area, and it kept this joining area of the lower grippy spring, it kept that really hard. So the first time I tried to slide it over my flashlight, it just broke. So I made myself a new one, I brazed it, and I annealed it, and I've cleaned it up right now. And I'm about to harden it, but I needed a tempering solution. So let me change the camera angle and I'll show you what I came up with. I designed this with blacksmiths and tool-minded people in mind. I know a lot of people make videos on how to build stuff like solder reflow ovens on YouTube, but a lot of those designs are overly complicated for the thing we want to do. What we want to do is take a piece of steel and heat it to a temperature and hold it at that temperature. The thing about tempering is that for most types of steel, you can hold a piece of steel at a certain temperature and it won't over temper. Obviously that changes when you get into like high grade technical steels, but for the stuff we're working with, if you hold it at 570 Fahrenheit, 300 C, it'll go to a dark blue and it'll be really good for springy stuff, which is what we're doing. Now, you can't overshoot the temperature, so that's where the electronics come in. But I tried to keep this as simple as possible. You only need a couple of parts, and it shouldn't cost you too much. So for instance, I got this online brand new for 20 bucks, something like that. Then you have an Arduino. I know this is kind of scary, but I've already written the code for you. So if you decide to build this project yourself, you really just have to buy all the parts, plug it together, and then run it. And this is the thermocouple. To my memory, it is a Max 6675 chip. Adafruit used to sell them on their website, but clones have been made all over. You can get them super cheap. I got this for under $10 with the thermocouple. All you want to make sure is that your thermocouple can handle about 100 degrees C over what you plan to heat. So we're going to go to about 300 degrees C, which is about 570 degrees Fahrenheit, which gets you to a dark blue. Any temper above that, you kind of get a little bit soft, and it's not really useful for anything, so a dark blue is going to be about the furthest we ever want to temper. So this thermocouple is rated to 600 C. It's a K-type. Honestly, the type doesn't really matter, and most K-type thermocouples are going to be rated way beyond 300 C, so buy the cheapest one you can get, and you're probably going to be okay. And the last thing you need is a computer. And yes, the biohazard sticker is required. So you may have noticed in that last scene that there's something sticking out of my toaster oven. Now this doesn't come stock. You can see I kind of just lazily chopped out a hole and I added a big aluminum heatsink. You don't necessarily need this, but I'll get more into it once we get inside this thing and the modifications that I did. But you're
going to want a heat sink or some way to dissipate the heat from the electronics that we're going to add. It's just a module, but if it gets beyond 125 C, at least for my module, the transistor that it actually uses shuts down, and then we can't control the temperature at all. So you're going to want to figure out some way to dissipate the heat from inside this. A great way to do that would be to buy a piece of KO wool and just stick it inside the electronic enclosure, but outside of the actual heating chamber, and just keeps the heat from dissipating through the heating chamber into the actual electronic bits. This toaster oven was actually so cheap that it didn't have any brain box or whatever. It just has this little timer dial, which I disconnected. When I wind it up, you can hear it tick down. And this is actually just very dumb electronics. So I had to add a couple of functionalities in order to be able to turn it off and control the temperature. Now, I've spared you the trouble of watching me try to open this one-handed and hold the camera with the other, but now that I've got it open, I can just show you how this works. It's actually pretty simple. So, with one exception, the white is neutral and the red is hot. The one exception is this wire right here, which I had to budge in. I'll explain that later. This whole thing runs off of two identical nichrome-based heating elements, and that's basically just a coil of wire inside a glass tube, and I can show you that. I have one of these right here. You can hear it rattling around, and if I can open this, there's just a coil of wire in there. And nichrome has a really predictable resistivity, so you can make a heating element like this really, really cheap. And all that is just a nickel chrome alloy. Sometimes there's a little bit of iron added in there depending on the alloy, but there's no practical way to tell in your shop. They both work the same, doesn't matter. And these little caps, I think, are ceramic actually. Let me see if I can get that to focus. Is it focus? No, it's not going to focus. Well, there you go. So there's two of those in here, one up here and one down below. And normally, in normal operation, if you just bought this from online, there's a little selector right here, and you can turn it, and it allows you to bake or broil or whatever. So broil turns on the top one, bake turns on the bottom one. Now, I want to turn on both because I want to get the maximum heat output. This is only rated for about 650 watts, so I wanted to see if I could get more. And all I did was I put them in parallel. So the neutrals in the back, I can show you that here, are already common together. So all I did was I commoned the hots together. And I have this just set on broil all the time. So when this comes on, this comes on. So we have 120 volts passing across both of these. Normally at 650 watts, that gives us about 5.1 amps, if memory serves. And so if we put two of them together, we're getting about 10 amps through. So you can still run this on a 15 amp breaker. Works just fine, get a lot more heat output. This little thing in the center, normally the neutrals coming back, I tied them together here. They just come back and they go back into the neutral. This is the plug at the back. Normally, this neutral would go here, and this neutral will go here. And all this is a crude thermostat. And inside there's a little blister of metal, and it's either bent like this or it's bent like this. And when it's bent like this, it is basically sitting flush against this inside wall right here. And as soon as that heats up to a certain temperature, as specified in the datasheet, that blister pops. And you can hear an audible click. And what that does is it basically breaks the connection of the neutrals and doesn't allow current to flow. And it's a very, very crude way of controlling the temperature of these things. So the reason that these cheap toaster ovens don't really work very well is because they have a really, really crude temperature measurement system. They only measure the temperature on this side. There's only one thermostat in this entire unit. But it also makes it perfect for hacking. So all I did was I took out the thermostat, let me focus here, and I tied the neutrals together, super easy. And then I cut the hot coming from the wall, and before it goes up and into the selector switch, I put it through an SSR. Now, when I said you needed to cool this thing, I was serious. You can see it's getting a little bit deformed here. This epoxy is rated to a pretty high temperature, and none of the components look like they're frying, but I'm going to be keeping my eye on this thing. I may need to redesign it in the future because it may just melt right out. And I suppose now is a good time to tell you that If you choose to do this project, you're on your own. I'm not to blame for anything you do. I've burned myself probably 40 or 50 times on the case of this thing. It's a cheap piece of junk. It's not made very well. And I'm working with mains voltage here. You don't see me going crying to the nanny state, so I don't want to see you blaming me, some asshole on a YouTube video, for hurting yourself doing, a project like this. But, I digress. The SSR, the solid state relay, that's just fancy speak for a really high current switch. So in the top, we have our signal from our Arduino. That's either 0 volts for an open circuit, that's off, or 5 volts for a closed circuit, and that's on. And all that does is it basically closes the hot line coming from the wall. One thing I want to mention is that you want to be switching the hot. You do not want to be switching to neutral. I don't really know why this is. My guess is that you don't want to break the neutral inside your circuit, or break it as little as possible. And that if you have a fault, you want it to fault on the hot and not fault on the neutral, maybe not damage the wires in your house. I'm not an electrician. That's just what I read on the all-knowing hive mind. So that's what I'm telling you. Break the hot. Don't break the neutral. It'll work either way, I'm guessing, but I don't think it'll work as well, or it may be more dangerous if you break the neutral. Now you'll also notice that this whole case is not grounded. So you're going to be really, really careful, because if either of these lugs touches the inside of the case, or if you have any unprotected connections that touch the inside of the case, this whole case is going to be live at mains voltage, and it's going to kill you dead. So be careful.
Now before I temper the real piece, I have a piece of the same hacksaw blade. I'm not sure if you can see that, but I did temper it to a nice deep blue. This was about 295 to 298 C. I think it peaked out at 298 C, which is somewhere just around 570 Fahrenheit. So I just hardened and tempered this, like you're going to see me do in a couple of minutes. And, you can tell, springs, let's see if I can get that in frame, it springs right back to shape. Now down here is where it's still annealed, because I can only harden about this much with the torch. But this is really strong. I cannot deform that plastically with my fingers. So I'm just going to heat it up with the old torch. I'm going to get it to about an orange heat, and then I'm going to quench it off in some water. Alright, well, I've got the Arduino plugged in, and I'm watching my computer with my camera, and I'm going to get this set up. So let me dock you guys in place. Here we go. All I'm going to do is take this tray with our piece on it, and if you remember when I hardened it, this little piece is, I was holding at my pliers. This is actually still a little bit soft, which is totally fine. It's not the springy part, not the part that we care about, so this can stay a little bit soft, so it's okay if it sticks up a little bit. We want to get the rest of this at the right temperature, so I'm just going to stick this inside. Oh, ate the rack. There we go. And I want to make sure that it's right underneath the heating element right here. So I want to have it about in the center. And then here comes the real finicky part, is getting this inside. So I think I'm going to stick it right in there, and then close that up. There you go, so you can see in there. Awesome. Alright, so I'm going to start recording, and I'll come back when this all works. Oh, by the way, right now it is on, but this dial is still engaged, so I'm just going to turn it to broil. And you might be able to hear it turn on. But there we go. It's going to start to heat up in a couple of seconds. There we are. so you can see that both elements are actually heating right now. All right, I'm going to time-lapse past this, and I'll see you guys on the other side. Now she's just a little hot to the touch, so I'm going to be ginger about it, but yeah, I think it worked out pretty well. So you can kind of see, if I can get it to hit the light right, let's see. There we go, there's a little bit of blue in there. Actually, I didn't clean off any of the scale after I hardened it, so you actually wouldn't expect to see that much blue, but I've done a couple test pieces before. You saw the hacksaw blade. I was pretty confident that this was going to come out, so I didn't have to use the color as an indicator. Usually when you're forging, you use the color as an indicator. But again, it doesn't always work for all types of steel, so you're going to have to experiment. I know that the program that I ran with the hacksaw blade, it was going to work with, in the environment that I had it with this type of steel, and it gave me a desirable result, and I think it gave me one here too. So I can, play with this. It's really something you have to feel in order to believe it, but this isn't as hard and brittle. I can bend it back and forth, but it's really not that malleable, which is good, because I don't want that to bend open on the flashlight. But proof in the pudding, as they say, is in snapping it on a flashlight. Am I right? It came out pretty good. Yeah, so that'll just fit over the brim of my hat. That's why it's not closed all the way. I'm happy with that. Well, thanks for tuning in, and I'll see you in the next video.
Quick addendum. First of all, sorry again about the shaky cam. You guys are off the mothership because my screen recording application doesn't work in Windows 10. Woohoo! So I got all my temperatures from anvilfire.com. This is a great resource. I noticed that the tempering colors for steel vary a lot depending on what site you go to. If you just do a Google image search, you'll get a bunch of different things, but most of the time you get about 295 to 300 for the sort of spring temperature you want. For a hammer or a striking tool, you'd probably go to like 270, maybe 280 if you wanted a little softer. And then for a cutting implement like a chisel or a knife, you'd probably go to about 250, or maybe if you wanted it to be a little more brittle, like a knife, you could go into the 220 range. For a cold cut chisel, I'd probably go to 250, 255. And then I just wanted to show you guys the code. So I will have this in the description somehow. There'll be a link to it. So all I'm using is the Mac 6675 library. I think I mentioned that before. And then I have my values here in a comment, so that if you change them, you can always refer back to my values that I use in this video. Obviously, this is up to you, getting the right oven and getting the right settings that work for you and the temperature of the room that you're working in, because a lot of these ovens aren't well insulated, so they might lose heat more quickly. So you're going to have to fiddle with these settings. It's unavoidable. All this does is set up the relay pin on 13, set up your SPI, which is, if you don't work with computers, don't worry about it. SPI is just a protocol for the Arduino. Talk to the thermostat, the thermocouple. Stat is a variable that we use to tell whether the relay is on or off, and this just keeps us from spamming messages. Don't worry about it. We set up the thermocouple, and then we set our high and low temperature range. And then, you can look at the Mac 6675 library to figure out how to set up your thermocouple and print it out. A little bit of error handling, and down at the bottom, this is our main loop. So we read the thermocouple temperature, we print it out, and then if it's below the low range, you just turn on the relay, and then you write high. So, the relay has gone high. We write that out. And delay for a second. Down here, if the input is above the high set range, then we just want to turn the relay off and cool down the oven as quickly as possible. And then, if we're between the low set range and the high set range points, then we want to hold. And all this does is it turns it on for 5 seconds and then turns it off for 1 second. And that's the sort of fluctuation that you saw. So this is pretty straightforward, pretty simple. I hope I explained that somewhat well. If not, you can always get yourself an Arduino, load this on using the Arduino software, and then not worry about it at all. Obviously, there's a lot of potential for tweaking. You could add PID control to this, but I found it really wasn't necessary.